So I'm really honored to be here and to have this possibility to talk to our community and to present some of our recent results. So let's start with the webinar. But first, let me introduce you my great team, which have worked with me at these to obtain these results. They are Hinglong He, Konstantinos Mattas, and Biagio Ciuffo at the European Commission Joint Research Center, and Marcello Montanino at my same university in Naples, Federico II. So here you can find also reference to the paper in which we presented these results. This is currently under review on Transportation Research Part C, but you can already download it from ACC. Well, so in this webinar, I'm going to present some recent results that concern the accuracy and robustness of adaptive cruise control algorithms and car following models when these algorithms or models are incrementally augmented with physics extensions, like, for instance, the perception delay, linear or nonlinear vehicle dynamics, or acceleration constraints. Their ability to simulate, that is, to replicate observed vehicle trajectories, has been tested here. So it is a specific focus here on simulation rather on design, for instance, of ACC controllers. And in particular, we have applied trajectories drawn by commercial ACC vehicles in control experiments. So, of course, why these? Well, we all agree that accurate simulation of mixed traffic, including human-driven vehicles or simply HDVs, and automated vehicles or AVs, is clearly crucial for the development of technologies for cooperative, connected and automated mobility, and for the assessment of their impacts on traffic efficiency and safety. And as a matter of fact, in many simulation studies, car following models and adaptive cruise control algorithms are applied just to simulate, to mimic dynamics of respectively HDVs and AVs. And so let's start taking a quick look at these two different classes of models. Well, you all know there are plenty of behavioral car following models in the literature, and they are mainly stimulus response relationships, which phenomenologically describe HDV's longitudinal interaction. In general, lower level dynamics are not made explicit, and they are all based on assumptions which rely on, let's say, partially unknown underlying human-driven processes. And this is the reason why there coexist several model formulations which have similar performances despite very different assumptions. But this is not new in science. This is called as equifinality or model indeterminacy. And we have made extensive calibration in the past, and there are so many studies in the literature about calibration of these models against HDV trajectories. And what we have seen is that performances in general vary more among trajectories than among models. And this is we will go back later on this because this is also confirmed by our results. But basically, we are saying that human-driven vehicles trajectories, or better, there are some human-driven vehicle trajectories which are reasonably reproduced by most of the models, while other trajectories, basically, all models fail to reproduce these other trajectories. So again, performances, it seems they vary more among trajectories than among models. Well, sometimes they have been used also to simulate AVs, and few examples of calibrations on AV trajectories also exist. And string stability, of course, is a big focus on these models, but Here, the focus is more on the relationship between microscopic strain stability and collective traffic instability. On the other hand, we have adaptive cruise control algorithms, and these are designed to be implemented, of course, in vehicles to assist drivers. They provide upper-level logics for automated longitudinal control of AVs, and we have explicit representation of control loop and lower-level dynamics. And often they have been applied to replicate AVs in simulation studies, of course, in mixed traffic situations. And what about calibration of ACC parameters, like example given controller gains against observed trajectories? Well, this calibration is not usually done because it's not customary in literature, because here it's more interesting to evaluate the impact of these technologies on traffic rather than to mimic commercial ACCs. And so in general, the design values are adopted and these parameters are not calibrated to reproduce an observed vehicle. And of course, string stability is a very desirable, I would say, required property for this model, even though at world level we are discussing whether or not including it in standardizations of vehicles. So in this slide, you see the three main questions that inspired this work. And I'm just going to read. The first one is, since car following models can be thought of as ACC upper-level logics, can lower-level dynamics improve their accuracy? And to what extent? When ACC algorithms are applied to simulate AV in mixed traffic simulation, what is the modeling detail level which maximizes accuracies and, of course, prevents overfitting? So is it sufficient, for instance, to consider perception delays, or we need to consider lower level dynamics or nonlinear dynamics, for instance? And the third question is, since car following models and upper level ACC algorithms are conceptually equivalent from a modeling point of view, one may wonder if any difference exists at all as to their ability to reproduce observed trajectories. So these are the main questions we try to investigate with this study. And to this end, we applied this modeling framework. You see here in this, can you see my pointer? I suppose.
Yes.
Okay. So you see here 5 base models. And we have incrementally augmented these models with perception delay, vehicle dynamics, acceleration constraints, and we have run calibration and validation of the models in order to understand what is the impact of these adds-on, and of course also to compare the different models. So let's start with the base models. Well, the first base model that we have adopted is the intelligent driver model. It is a very well-known model. I don't need to tell you anything about this model. And it's just to observe that, of course, this is crucial, and we will see later that we have applied this, the desired distance, which is part of the IDM model, also in a linear controller. The second model we have applied is a completely different model. It's the Gipps model, which is a safety-based model, which basically provides the speed for following instance in a way that a vehicle can reach a safe stop, even in case of a sudden acceleration of its leader. And then the third base model is a simple linear control law with a constant time-headway policy. I don't need to spend any words also on these. And then the fourth model is another type of model we have introduced here. It's a very simple intuition, very simple extension. We just coupled a linear control law with the IDM desired distance. And of course, if we look at the first part of this desired distance, basically is a constant time headway. And so we wanted to evaluate whether the third term which is deemed responsible for, let's say, the intelligent braking strategy of the IDM model, can improve performances of a linear controller with a constant time-headway policy. And finally, we have derived a fifth model, a fifth ACC controller, that basically is a linear controller plus the Gipps equilibrium distance speed function. This equilibrium speed distance function has also been very well studied. If we solve at equilibrium the Gipps model, and basically we derive the steady-state solutions of the differential equation systems made by the Gipps equation and the equation of motion, we obtain this relationship, which has a very nice interpretation. Basically, it is a constant time-headway policy plus another term, and this term is just the difference between the spacing, the stopping distance by the follower minus the stopping distance of the leader. So in case this difference is positive, so this means that the follower is not underestimating the decelerating capability of his or her leader, well, we have a conservative driver and we have a convex distance speed function, which provides this fundamental diagram. In case instead of an aggressive driver, so when the follower underestimates the deceleration capability of its leader, so it's very confidential with its capability of braking, well, we have this other shape of the distance speed function and very well known inverse lambda shape for the fundamental diagram, which accounts for unstable traffic. And so we wanted again to see whether this third term can improve the constant time headway policy of a linear controller. So we added to this base model first the perception delay. Of course, the perception delay is added to all inputs of our models. And of course, we consider the case in which the perception delay is null and the one in which is a constant positive value. Then we added vehicle dynamics and simple linear dynamics just with an actuation delay and classical nonlinear dynamics. And it's not the case of going into details. And we added acceleration constraints, and specifically we added constant boundaries for the acceleration and deceleration, and the value given by the MFC models. The MFC model, the micro-simulation free flow acceleration boundary model, which has been developed at the JRC Joint Research Center. And of course, we adopted the ballistic assumption for integrate all these models. So at the end, here we have just the 18 variants, which comes from the all possible combination of these physical extensions. You see on the first line the base model, so it is just the IDM with no extensions, and then you see the first triple is just as a acceleration constraint, so a constant acceleration constraint or the MFC. And then the following triples add linear controller, non-linear controller, constant perception delay, and then the combination of perception delay and linear controller, or again, the combination of constant perception delay and non-linear controller. So, and of course, we have done these for all 5 base models, so that at the end, we came out with 90 model variants. So, what about the data? The data are the ones which were gathered in a campaign made by the colleagues of the J Joint Research Center. On the ASTA0 proving ground, you see here, and specifically the experiments were made on the black path, and you see here the road slope of this proving ground. And they made 7 experiments in which we had 5 vehicles. The first one, it was always the ODA8. And then we have other vehicles which follows with different orders among the different experiments. And the important thing is that here the leader was instructed to follow a certain speed profile, and all other vehicles were using the ACC during the whole campaign. So the drivers in these vehicles could only, of course, take care of the steering wheel, but not of the acceleration and deceleration pedals. And these are the resulting profiles. You see here the speed profiles on the left column and the spacing profile on the right column. And you see that the first 5 experiments have quite similar patterns. You have acceleration, deceleration of vehicles, while the last 2 are much more noisy. And this was made, of course, to stress ACC algorithms of the vehicles. And of course, these are open data, so you can download at this link. Well, so how did we perform our comparison? And we applied this framework, which encompasses both calibrations and validations. And so we have 4 follower vehicles and in 7 experiments for a total of 28 ACC trajectories. And as we've seen, we have 5 base models for 18 variants, so 90 models. So we came out with more than 2,000 calibrations. But we perform also validations, cross-validation. So what does it mean? Imagine we have a car model, let's say a Tesla. For a Tesla, we have available 7 trajectories. So 1 trajectory is per experiment. So we can calibrate whatever model, each one of our 90 models on one of these 7 trajectories, and we can use the calibrated parameters to simulate the other 6 trajectories. In this way, we can test whether the calibrated parameters are robust and can use also to simulate the other, the same car model, but in different situations with different leaders' trajectories. So basically, for each car model, we have 6 trajectories, 6 cross-validations. And so we can perform for each model 28 times 6, that is 168 cross-validation per model, for a total of 15,000 cross-validation. Of course, these are one-shot simulations, so they are much more easier to perform than calibration. And about calibration, I will not spend time on this, just to say that in a recent work, we have verified that the normalized root mean square error on speed, spacing, and acceleration is the most preferable goodness of fit function among the Pareto efficient ones. We base these on both theoretical and experimental arguments based on a very vast calibration campaign over different data sets and using all the GOF used so far in the field literature. And so we are quite confident that setting is a robust one, but we have also confirmation of these in the results. So, and these are the first results that we got. So here you see plotted the normalized root mean square error on speed, spacing, and acceleration for the 5 base model. So, sorry, for each car model for the 7 experiments. But of course, you may see that there are several bars for each car model, and this corresponds to the leftmost bar is the best performing model. So it's the result in terms of normalized of our GOF of the best performing model, while the rightmost column is the worst performing model among the 90. And the 5 bars in between refers to the 5 base models. So the models with no extensions. Well, if we look at these results, so together we see that my claim that the variability of performances is driven more by the leader's trajectories than by the model itself, which actually is not my claim. It's also my claim in a very old paper, but has been confirmed in many experiments, has also been confirmed here in these experiments, and we have quantified this impact. You see here, we have calculated the first order sensitivity index. That is a way of understanding what is the first order impact of, in this case, of 2 input factors we have, so the trajectories and the models on the variability of the outputs. And we see here that results are quite clear. The first order impact of trajectories is 0.8, while the models account for the 0.06% of the variability of our output, so our calibration results. Of course, this does not sum to 1 because the model is not that the input-output map is not a linear one. It's not additive and linear. So I think there's no time to compare models and to see what we may say a nice thing about these very nice car models, but anyway, let's move to the second main results. In this diagram, you see instead are represented the 90 models. So in this diagram, we can compare the models. And we can also appreciate the effect of adding, of course, the physics extension to these models in terms of accuracy. We will see later in validation how these extensions instead affect robustness of results. Well, here with the box plot here are represented not the absolute value of the normalized root mean square error, so the calibration performance, but its relative error. So it is standardized over the best, so the minimum value of the GOF among all 90 models. This means that you see each box plot here. Let's take the first one, which refers to the base model, the IDM. Well, we have 28 points, which are the 28 calibrations results against the 28 trajectories, but we are not reporting here the absolute value like in the previous diagram, but this relative. And this is clear. We need to do this in order to compare calibration result made on very different trajectories, so with very, very different results. And it is the only way to compare these 90 models. So we can see a number of interesting on this diagram. Well, first of all, we can see that here I remember you in this first triplet of models we have just added the acceleration constraint. In the second triplet, the linear vehicle dynamics, then nonlinear vehicle dynamics, perception delay, and then perception delays plus linear dynamics, perception delay plus non-linear dynamics. So we can appreciate some results that hold for all models, and in particular that in the linear dynamics you see here, but you see also here, and so in all models, they improve, we might say that sensibly improve model accuracy. And we have a similar result for the nonlinear vehicle dynamics, though in this case situations vary from one model to the other. So we have in apparently here an improvement with respect to at least to some values with respect to the linear dynamics, while this is not clear for all other models. So we will see that the IDM it's a singular behavior with respect to the other models. We can also say that the impact of perception delay in all models is similar to that. It's the same order of magnitude to that of linear vehicle dynamics. And when we combine in all models perception delay and linear vehicle dynamics or nonlinear vehicle dynamics, of course, the contribution, the whole contribution is less than the sum than the individual contribution. So these are just some of the possible consideration we can make on this diagram. But of course, we can also compare models. And here we see quite easily that the best performing model, so the model, I remember that is better at reproducing the observed commercial ACC trajectories is the Gipps model. And this is not actually a true surprise because the Gipps model is a safety-based model. So if we imagine that the unknown ACC algorithms which are implemented in commercial cars aims at mimicking human behavior, or at least a safe human behavior, it is no more a surprise that the whole Gipps model is the best, is the one that is able to best reproduce these trajectories. And we can also see that if we, of course, in this case, when we couple the Gipps model, or better, the equilibrium distance speed function of the Gipps model with the linear controller, though we observe a number of outliers, if we compare the median values of our results, we will see that these equilibrium speed distance function actually improve a little the CTH policy of a linear controller. Well, so we can move to validation results, and here you see plotted for all 90 models a specific measure of validation. We have told that once we have calibrated a car model on a specific trajectory, we can validate. We can run simulation on the other trajectories. Of course, it may happen that with the parameters calibrated in different trajectories, we can observe an accident, so a collision. And in this diagram, we have just plotted the number of collisions for each model variance, which happened in the cross-validation experiments. And this is clearly a measure of the robustness of the model. And we did this also for a number of GOF functions, also to understand whether the normalized root mean square error was the most robust GOF function in calibration. And this is actually what we have observed. In particular, we observed that the tails coefficient and the normalized root mean square error that have been indicated in this recent paper as the most preferable among the Pareto efficient ones, confirm these results, and they prove to be also the most robust with regards to the collisions. So with those GOF, we obtain the most robust and transferable set of parameters. Concerning, of course, different models, we observe here, very interesting, that the IDM is by far the most robust model. And so its parameters calibrated on some trajectory can be used also in other situations, followed by the Gipps model and by all other linear controllers. Again, here we see that there is a good behavior of the linear controller when it is coupled with the Gipps speed distance equilibrium function. And so we arrived to the conclusions. And so basically, we have presented in this work a comparison framework, which allowed us to compare behavioral conforming models and ACC algorithms, augmented with lower level dynamics of increasing complexity. When, of course, these two type of models algorithms are used to simulate ACC trajectories. I do not mention the reason why we have adopted the ACC trajectories, and the reason is simple because, of course, we have plenty of calibration and validation on HDV's trajectories, but very few on ACC. But as I was saying, these models are used in simulation studies to mimic behavior and to evaluate the impact of these both HDVs and AVs vehicles on the safety and efficiency of mixed traffic. And so we wanted to make this study on AV's trajectories. And further, of course, because we expect that these trajectories are more predictable, so we do not have stochastic variation of behaviors like we have with human drivers. We also expected that these trajectories would have allowed us to have a more fair comparison among models and less noisy. So we have proposed two different spacing policies for ACC controllers, which have been derived from very well-known microscopic models. And of course, the calibration have allowed us to assess the contribution of each physical extensions to the base model accuracy. Well, performances of car following models and ACC algorithms, once augmented, also have been compared. And we have seen the IDM and the Gipps car following models reproduce ACC vehicle dynamics more accurately than linear controllers. I mean, let me say that this is not really a surprise. And across all 90 model variants, the Gipps one was definitely the most accurate. And concerning transferability, well, the IDM outperformed all IDM variants outperform all other models. So these variants are the most robust ones. We also proved that the normalizing root mean square error improves model robustness and transferability of related calibrated parameters. And we have shown these, I mean, at least in this experiment, using the number of collisions occurred, as we have seen. And concerning the effect of adding this physical extension, we have seen that adding linear vehicle dynamics to a base model largely improves model performances. In this specific experiment, and with the nonlinear dynamics considered here, this result seems not so good with nonlinear dynamics, but I mean, I would be quite cautious with these results. And we have also seen that the perception delay improves accuracy by the same order of magnitude of linear dynamics. And of course, the combined effect of linear dynamics and perception delay is less than the sum of the single contribution, but of course also this was expected. And finally, let me say that we have seen that we very well know that car following models have limitation concerning the ability of reproducing trajectories. And from all studies, we have seen that there is a sort of threshold under which we are not able to go. And this has been explained in various ways. And it depends, of course, on the many limitations, the theoretical limitation which have these models. But we might have expected that this threshold was different in case we try to mimic ACC from commercial vehicles. Instead, we have seen that the situation is almost the same, even with AV trajectories. So we conclude that these models, so both car following and ACC controllers, which have been used in simulation in a very effective way to assess the impact of various types of transportation policies, at the moment do not seem really sufficiently robust to assess the impact of technologies which are going to influence vehicle operation, especially in a second environment, so in connected, cooperative, and automated mobility. So this is my last conclusion. I thank you very much for the attention.
Okay, thank you. Thank you for the nice presentation. So now we start the Q&A session. You please feel free to unmute yourself to ask the questions or leave the question in the chat box. Dr. Punzo, we already have 2 questions in the chat box. And the first one is from Ms. Fang. Her question is, can you please introduce more about the empirical trajectories, like the scenarios those vehicles are in? Are they on a freeway or signalized roads? Are they in a dense traffic or congested traffic? Thanks.
Yes, no, these are control experiments. So the vehicles are run in this proving ground, which is a proving ground in Sweden, just a zero proving ground, and there is no true traffic. It's a controlled experiment in which a little vehicle moves, and the vehicle is instructed. I mean, the driver is instructed to follow a specific speed profile, and then all following vehicles are driven by just ACC controllers. So the drivers can only use the steering wheel, but not the acceleration and braking pedal. But I would encourage my colleagues at JRC who actually performed the experiment to say something more about this experiment. I don't know if okay. Someone of the, I cannot see the
chat box, the top right corner.
Top right.
Okay, there we go.
Okay.
Hello.
Hello. Yes.
Hi, Vincenzo. Biagio Ciuffo from the JRC.
Hi, Biagio.
No, I just wanted to, confirm what you said. I think that the explanation you provided is sufficient. Also because details about the experiments are available in the literature. So more details can be found definitely under the Open ACC open data program of the JRC, where we publish all the results of the experiments that we carried out with the adaptive cruise control and other levels of automation vehicles. Thanks.
Thanks to you. So the other question.
Okay, another question from Lena. The desired time headway is an essential parameter when modeling ACC, which is not explicitly present in the Gipps power volume model. So how do we account for this when modeling ACC using Gipps?
Yes, right. So you can see the slides, right?
Yes.
So let's just. So in the Gipps model, basically we have the reaction time that is not a true reaction time, so it's not able to actually. It is not an actuation delay, but it's just it is defined by Gipps as an apparent reaction time. So actually, it is a time delay which is used in a predictive way to calculate the stopping distance of both leader and so better to calculate the stopping distance of the follower. So this reaction time is the sum of these two aliquots. Usually it's called tau, and this is the same as a constant time headway in constant time headway policy, or also in the IDM model. This shows that actually this speed distance function here is just the same of the constant time headway policies plus this term, And as I was saying, this term is just, so the first, if we multiply these within the parentheses, we obtain the first term is just the spacing distance of the leader, the stopping distance, sorry, of the leader. And this is the stopping distance of the follower, or better, is the expected stopping distance of the follower, because this is the maximum acceleration of the leader estimated by the follower. And so we wanted to understand whether adding this term basically to the CDH, we had improvement or not. I hope this explains the question.
Okay, the next question is from Danjit. Please go ahead.
Oh, okay. Thank you very much, Vincenzo and Biagio, for the nice work. It's very interesting. I have one question. So you mentioned here you are considering the linear dynamics, for example, the several elements like the delay and acceleration bounds. So I'm wondering, is it possible to directly capture these elements? So here, I mean, of course, one way we have is what you did here, like to calibrate. But is there any way we can directly measure those?
Yes, of course, we can directly measure these values. But what we have seen in the past is that when you use car following models, and your objective is, of course, to have a model which closely resemble actual trajectories. So your objective is to have the best possible model. So what you actually do is to calibrate this model. And once you calibrate this model, it happens that the calibrated parameters values often are completely different from what you can observe in reality. And this is very clear from a theoretical point of view, a modeling point of view, because what actually do when calibrating parameters is just covering let's say the epistemic uncertainty of the model. So the model is not perfect, of course. Let's say it's wrong. So you cannot feed your model with input taken from reality, because you would need a perfect model to fit it with the true value of the inputs. Instead, if you have an imperfect model and you fit it with, let's say, perfect inputs, you obtain a bad result. So you are forced to calibrate your models, and the result is that the calibrated model is very different from the, let's say, the true observable value of these parameters. And we have experienced these also in this case, for instance, with the nonlinear dynamics and road load coefficients. We had the value measured on the roller bench, and if we calibrate these values, we come out with unfeasible value of these values. It is clear that here there is a very delicate balance between calibration of parameters and overfitting, because if you let these parameters to vary within very wide ranges, of course you are risking, you have the certainty of overfitting models. So it is a very difficult compromise you have to find. So this calibration is not as easy as it may seem.
Yeah, that I fully agreed. So I'm curious, are you aware of any work or that directly, for example, quantify like the delay there, and also I think for the acceleration bound. So yeah, from the reference I see that, but for the delay, is it possible to measure that, for example, using the open ACC data?
Yes, I mean there are a number of studies which measure delays of all types. I mean human factor studies, both for human-driven vehicles and ACC. If this is your, I mean your question. I mean if you are referring to the delay of the human driver, the other delays, so the actuation delays are also very well known in the literature. So I can provide later references to you if you want.
Okay, yeah, that's great. Thank you.
Thank you. And Suyuan, please go ahead.
Thank you, Professor. This is Suyuan Gong from China University, and thank you for your presentation and giving a lot more insight about how to combine the modeling things to the real world. And my question is still a little bit similar to Danjue, and my question is still about the perception delay. And could you share some, I mean, your calibration result about this delay? Because, you know, in this kind of commercial vehicle, each manufacturers use different perception, I mean, the mechanisms. So maybe it will cause different kinds of delay. And also in our university, we also have this kind of autonomous vehicle. And when we test it, we can find that, you know, the perception delay is always varying. Sometimes it's not a fixed value. So can you share something about that? Thank you.
Yes, I can show you the values that we have used to calibrate this perception delay. So it was this last slide. So concerning perception delay, I cannot find it. Oh, well, I think it is this TA. I'm not sure. Let me check. Sorry. Tau P. Sorry. Tau P. So we adopted these boundaries. So between 0.1 second and 0.8 second. But at the moment, I am not able to give you which are the calibrated results. I'm not here. I'm sorry, but these are the ranges we used, and we thought to cover reasonably commercial ACC systems.
Got it. Thank you, Professor.
Next, Zhou Yang, please.
Hi, Professor. Yeah, thanks for the gorgeous presentation. So I'm Yang Zhou from University of Wisconsin-Madison. So I do have two questions. The first one is that since the OpenACC dataset has like different types of vehicles, or I mean like different vehicles from different automobile manufacturers. So do you have like unanimous conclusion for all types of vehicles, or your result is basically for specific made of vehicles? That's my first question.
Yes, I mean we did not investigate it actually. We do not want put the accent on performances of different models. But if you look at the data, there are some differences I mean there are the trajectories of some specific car model from a manufacturer that let's say are more difficult to be mimicked, to be reproduced by our models, so are less, I would say, less predictable by our models. But we not concentrate on making this this comparison, not to make any type of advertisement, of course, or counter advertisement again. This different car type.
Yeah, cool. And another question is that since you have like a lot of parameters such as the delays, like the min-max function, something like that, right? So it's super complex, seems to be. So how do you really calibrate them? Since some Calibration models are kind of like complex.
Yes, we used a genetic algorithm, and the genetic algorithm, of course, it was written in Python, and we, of course, also try to validate this algorithm to see whether it was really able to find a global minimum. I can maybe share with you this one. Sorry. So I hope you can see these diagrams.
Yes.
I'm not able to move. Okay. So here you see we perform a number of calibration for the same models, and in order to verify whether we obtain, let's say, always the same result. I mean, this is a very simple explanation. And so our result confirms the goodness of this calibration setting. I mean, I can send you the paper. I mean, this is better explained here. And we basically calculated the coefficient of variation of these results in order to see whether there was a big dispersion among the calibration of the same model on the same trajectory. But we have seen that actually with almost all models, so these coefficients of calibration, it's very small, and so we reasonably have a good setting with a good calibration setting. And concerning instead, or better, a good calibration algorithm. Instead, concerning the normalized root mean square error, as I was saying, we have verified in a previous paper that this goodness of fit function is the most preferable one in a number of cases, and we also provided a theoretical justification for this. So the paper is this one, and you can find there much more. And we have also shared the codes for calibration in this other paper, both the codes and the data sets. So our idea is that whatever new scaffolding model is proposed, whatever new calibration setting is available, one can feed this framework, one can plug into this framework and make the most of all the work that we have done. So, and try to understand whether the new scaffolding models performs better of all the other, which have been compared on a big number of trajectory data using a very high number of different goodness of fit function. So I invite you to if you're interested in this topic, to download the codes, and again, you can test whatever you want. You can test a new goodness of fit function, you can test a new model, an ACC controller, or whatever.
Sure. Thanks so much.
Okay, our next question is from Dr. Lava. Please go ahead.
Hey, Vincenzo, thanks for stopping by our webinar. Really glad that you can make it.
Thank you.
Could you talk a little bit more about the part where you said that the leader trajectory has the biggest impact on the variance? I'm not sure.
Yeah, sure.
I got that.
Yeah.
And does that mean that the model is not very important,
or that all models are not very good? This is another interpretation. So it seems that if can you see the screen?
Yeah.
If you look at the variability of performances for given vehicles. So let's concentrate on these, for instance. You see that the difference between the best model and the worst model is not so big.
Right.
So all models have quite the same performances, and if you make this exercise for all the experiments, so all vehicles in all experiments, you would see that this variability is much less than the variability due to the trajectories. So if you, for instance, take, I don't know, this model, which is the linear control model with the Gipps, and you see performances of this model for this car, and you compare with the performances of the same model on another trajectories, I can try to, yes. You see that this difference is much bigger than this. And of course, you may say, I've chosen in the right way the example, but this is a way of objectively and quantitatively measure these. So basically, if you take your, let's say, your input-output table, so let's say you have the models here and the trajectories here, and every single cell is just the result of the calibration of that model for that trajectory. So you have an input-output mapping, and you can use, of course, the sensitivity index is no more than a standardized regression coefficient in a multiple linear regression. And so basically what are you doing is this one. You take, you take xi, that is, let's say you take one trajectories, and you calculate given that trajectories, the average of all of the performances for all 90 models. Okay, then you take the variance among, so once you obtain this average, you take the variance among all trajectories. And you compare these variances, which is a conditional variance, of course, conditional on the model. You compare this with the unconditional variance, which is just the variance of all your table, which is so this gives you the first order impact, so without interaction effects. And it is very clear here that the trajectories explain much more of the variability of the data than not the models. So it seems that my first consideration was that there are some trajectories in which all models are very good, and some trajectories which all models fail to reproduce quite good. So this suggests that these models, there is some missing part in this model. So there is some, of course, latent behavior, hidden hypothesis, and we know very well a number of these hypotheses, simplistic hypotheses of these models, which prevent this model to perform in a very good manner, whatever the leader's trajectories.
Okay, yeah, that makes sense now. That's interesting.
It's a matter of the explanatory power of this model. So maybe if we include in this model, I don't know, a variable reaction time which is variable with time, or maybe we include multi-anticipation, all the very well known deficiencies of our models. Maybe we could lower this effect, so we can increase this first order effect and decrease this other. So we would see that the explanatory power of our models are increased.
So we can say that we need better models then, or more explanatory variables?
Of course. And this, to some extent, justify our last conclusion. We think that this model are not very good to, of course, to evaluate the impacts of SECAM technologies because of all these deficiencies.
Right.
So we have used them with great success, evaluate the impact of other policies in traffic usually. But when we go to specific behavior, like the one which includes the lower level dynamics and more detailed stuff that we want to evaluate, we think these models are not that good. So we need to do something, of course, and we are doing something, of course.
Good. So you have a clear path forward for your research. That's excellent.
I mean, when I say we, I mean the community. So
yeah,
I think this is quite clear, not only me.
I see we're running out of time, so maybe we have time for one more question. Oh.
Yes. I think Dr. Bain just raised his hand. Please go ahead.
Yeah, okay. Just as always, a very fascinating talk. Thank you. And your observation that some trajectories are poorly fit by just about any car following algorithm, that is consistent with some of what we're seeing in our empirical loop detector data, which really sort of boils down to, even though traffic is congested, there seems to be some drivers who aren't actually car following. And that might actually be why some of these drivers don't fit car following models, because they really aren't car following. And then it's so I'd be curious about your thoughts on that, and then just sort of a second comment or observation. Could you speak to the fact that the real adaptive cruise control algorithms are probably far from homogeneous? So it's almost as if different vehicles are following different car following models.
Sorry, are you asking to comment on the fact that about the homogeneity of ACC from different vehicles?
The heterogeneity of
the heterogeneity. Yes. What we see here is that basically ACC among vehicles have very different behavior, and of course this also very well known. And of course you can also, we can ask to colleagues, but I think that of course in this ACC, in these vehicles, you can choose also a setting. Typically, you can choose whether adopting a short headway or a longer headway. And I'm sure that the chosen setting was consistent among all vehicles. And notwithstanding this homogeneity of setting, we can observe very different behavior and this is proved by the fact that the same models cannot reproduce in the same way with the same level of accuracy this ACC behavior. So for sure. So if I may comment on these, we have always thought that the human-driven world is a very heterogeneous world, and that this heterogeneity would have disappeared once we would have in place commercial ACC automated vehicles. It seems to me that this is not going to happen, and the task for modelers is the same as before, even though because they do not know the true logic which are implemented in ACC. So unfortunately for we modelers, heterogeneity is not going to vanish.
I would be correct. I would agree with that, with one deviation, which is I think in the long run, we in the research community should probably make the case that, the manufacturers need to all adhere to some common standard to achieve, as long as we have heterogeneous adaptive cruise control and automated vehicles, that's going to lead to suboptimal flows. So there is probably a need to standardize across manufacturers as these become more mature.
Recording in progress.
Yes, I can.
Determines if there's a threat collision, and if so, what to do about it. And then that's issued to the pilot in their display, and then the pilot decides if they're going to follow that or not. And
sorry,
we were disrupted.
So I can tell you for sure, Biagio can tell you if he's still connected much more about this, because actually this is what is going to be is actually discussed at the moment at the UNO level about standardization of vehicles, because the problem here is to understand which is the safety level which these vehicles have to provide. And so here again, the problem is it has been agreed that it should be the same safety level, at least at the beginning. Of course, we expect that safety will increase, but at the beginning, it should be the safety level provided by, let's say, by a careful and competent driver. So now there is a research effort, a call at European level for devising a human driver modeling, which is able to define which is the, let's say, the safety level of a human driver. And so you're right. That's we should arrive to a sort of standardization, not in the algorithms, because everyone can of course devise its own algorithm, but of course we need to know that vehicles obey to some basic rules, and they do not go, they do not provide. I mean, they do not disrupt traffic and do not provide problem to traffic efficiency, of course, that which is something that is not I mean, it has to be, of course, enforced to car manufacturers.
This is already being discussed at the European Union level?
Not, at the moment, this is discussed at the UNECE level, so at the world level, and Biagio is leading. Biagio is leading some tables on this on behalf of the European Commission. So I don't know if he...
Yeah, that's very interesting, because that sort of thing should happen in the US as well. But I guess Europe is ahead of us.
But US is at the table. US, Japan, they are all at the same table.
Yeah, the problem in this case is that people sitting at those tables are not really aware or interested, to a certain extent, to traffic problems. Because at least until now, requirements for vehicles are always focused on safety. So it is very difficult for them to understand the impact that vehicles can have on traffic flow now that their operation is automated. So this year, we, for the first time, were able to push the idea that, for example, one of the requirements for vehicles is that they should be string stable. But in order to let them understand what this was meaning, it was really a challenge, because and the problem is that until you don't put a requirement to the basically automakers about having string stable vehicles, or in any case traffic efficient vehicles, they don't see the problem. They see one vehicle, it needs to be safe, whatever the effect on traffic, for them is irrelevant. And they will not listen to us. They will just listen to the regulation that will tell them the requirement for building their vehicles. And this is a big problem for our community, in my opinion. Yeah. But okay, by working and showing, thanks, I think this is we can work in this direction. Thanks, Vincenzo.
Thanks to you for all this work.
Yeah, so string stability is one aspect that I'm happy that it's being pushed. But the other is efficiency, right, as Vincenzo. And they're not always hand by hand, stability and efficiency. But I guess we'll be getting there.
Yes, you are perfectly right.
Mm-hmm.
Excellent.
Okay,
very good
great.
Discussion.
We have a very nice and long discussion, which was great, and show how we love your presentation, Dr. Punzo. Thank you again for your time. And for all the audience, thank you for coming until late night. We wish you a nice weekend and hope to see you next week. Bye-bye.
Thank you very much. Again, bye-bye. Thanks to everyone.
Thank you.